Welcome to this explainer. Today, we're mapping out the complete data-to-decision journey of AI, specifically focusing on natural language processing, or NLP. We're going to dive straight into the core of how machines actually parse, understand, and infer meaning from human text. It's fascinating stuff, so let's get into it. Here's our roadmap for today. We'll be covering the shift from perception to reasoning, how we prepare data, the inner workings of a neural network, Naïve Bayes probability, support vector machines, and finally, how we actually evaluate model performance. All right, Section 1, AI, from perception to reasoning. You know, the true evolution of AI isn't just about perceiving an image or recognizing a word anymore. The real game changer is this critical transition from simple perception to complex reasoning. We actually want the system to logically infer outcomes. It's the difference between a machine just seeing the letters that make up the word apple and actually understanding that it's a fruit you can eat. Moving on to Section 2, preparing data for machine learning. Before an AI can reason, we have to feed it, right? And cleaning data for NLP is a pretty rigorous process. First, we have to strip away all the noise, so removing special characters and stop words. Second, we deal with missing values. If there's a blank space or a nan in our dataset, we have to replace it mathematically, maybe with a 0, a max value, or an average. And finally, we encode all those mixed categorical strings into straight numbers. Look at this clear before and after of the preprocessing phase. On the left side, you've got this messy, real-world information full of blank gaps. But on the right, that's pristine, clean data. The missing values are zeroed out, strings are numerically encoded, and it is fully ready for the machine to digest. So once the data is clean, we still have words. But here's the thing. Math models definitely do not speak English. So we use these data representation methods to turn our text into dense numerical vectors. Whether we're using a statistical approach like Tf-IDF or neural network-based embeddings like Word2Vec or fast text, the ultimate goal is exactly the same. We are literally translating human language into the mathematical language that our algorithms can actually understand. Okay, Section 3. Let's step inside a neural network. People love to call neural networks a black box, but let's peel back the layers here. From a purely mathematical standpoint, if we feed the network a simple training vector of 2 and -1, what exactly is happening under the hood? Well, we can actually track the math across 4 exact steps. First, we initialize our weights. Second, we calculate a forward pass to make a prediction using an activation formula, like a logistic function. Third, we initiate the backward pass, basically checking how wrong we were, to calculate the error, which we call delta. And step 4, we update those initial weights using a learning rate. Let's actually see that in action. Looking right here at this table, we can track our training vector of 2 and -1. Notice how the input multiplies against our initial weights, which are 0.5 and -4. That result then passes through the logistic function formula, giving us our initial forward pass output scores, 0.876 and 0.085. Essentially, the machine just made its very first mathematical guess based on its initial untrained state. Now, here is where the magic happens. After calculating the error from that initial guess, the network applies a learning rate, in this case 0.1, to the error delta. Through this calculation, our original, completely arbitrary weight of 0.5 perfectly updates to 0.506. I know it's a tiny shift, but it's absolutely crucial. It proves the machine just mathematically adjusted its understanding. It literally just learned. And it's going to repeat this process for millions of cycles. Moving right along to Section 4, Naïve Bayes and probability. Let's leave the intense math of neural networks for a second and play detective with this historical car theft data set. We have a few features: the car's color, its type, and its origin, and our target outcome was it's stolen. Now, Naïve Bayes makes a big assumption here. It assumes all these features are completely independent of each other and relies purely on the historical probability of each trait. So, applying this Naïve Bayes logic, we can pose an exact micro-mystery to our algorithm about a brand new, unseen vehicle. If a car is red, a classic model, and domicile origin, what are the chances it gets stolen? To solve this, the algorithm just calculates the probability of each independent feature resulting in a yes. It literally just multiplies the historical fractions together. So, the probability of red given yes, times classic given yes, times domicile given yes, times the overall probability of yes. That gives us 3/5 times 1/5 times 2/5 times 5/10. By crunching these independent fractions, the algorithm takes a Thrive statistic and turns it into a solved case, giving us the exact probability of theft. Pretty cool, right? Let's jump to Section 5, Support Vector Machines Explained. Now, the core idea of a support vector machine, or SVM, is finding a mathematical boundary that cleanly separates different classes of data. But notice the contrast here. For simple data, it uses linear separation, literally just drawing a straight line margin. But for messy, complex, real-world data, it relies on nonlinear separation. It applies a mathematical kernel function to literally bend the data into a higher dimension where a straight boundary can finally be drawn. It's like a space-bending trick for math. Finally, Section 6, Evaluating Machine Learning Performance. So we've built our engines, but we never just trust the machine blindly, right? When we test an AI, we use these precise metrics to evaluate exactly where it succeeds and where it's making false assumptions. Accuracy is easy. It's just overall correctness. But precision? That tells us, out of everything the AI claimed was positive, how many actually were. Recall flips it. Out of all the actual positive cases in reality, how many did the AI successfully find? And then there's the F1 score, which gives us a harmonic mean, perfectly balancing precision and recall when we need a stable middle ground. Let's look closely at this confusion matrix for a spam versus non-spam classifier. Out of 65 actual spam emails, the model got 45 true positives, but it missed 20. Those are our false negatives. Out of 35 non-spam emails, it correctly identified 30 true negatives, but falsely flagged 5 as spam, our false positives. By mapping these exact real-world test results, we can mathematically derive our precision, recall, and that F1 score using the formulas you see here. It perfectly visualizes the AI's exact margin of error. As we wrap up this explainer, I want to leave you with this final thought. We've gone through all the math from perception to reasoning, but think about this real-world scenario. If you are building an AI to diagnose a critical illness, which metric actually matters more? High precision, meaning you never scare a healthy patient with a false alarm? Or high recall, meaning you accept some false alarms just to guarantee you never ever miss a genuinely sick patient? Choosing the right evaluation metric isn't just an academic math problem anymore. It is the very thing that makes or breaks an AI's real-world impact. Thanks for joining me on this journey into the architecture of NLP and artificial intelligence. Catch you next time.